Let's look at alkene bromination part 2. So in the first part, I did talk about 2 steps for the alkene bromination. And so there is cyclic bromonium species produced, and then electrophilic nature of the bromine. Those are the key things. And today, now, we are going to look at the steric specifics on it, stereo specifics. Let's look at this question that I gave you last time in the previous video. So we had this asymmetric alkene and then the bromine, not Br2 but Br and Cl given. So now, because of the electronegativity nature, Br becomes the delta plus specifically, and then the pi bond attacks on the electrophile Br delta plus, and that's how you make the cyclic bromonium in this scenario. Now here, because we put it into the top, and then we can put the cyclic bromonium on the top of the flat molecule of cyclopentane ring. It's methyl cyclopentane, right? And the chloride becomes the nucleophile, right? Because Cl minus. So in this scenario, the chloride only attacks to the better carbocation. There are 2 carbocations possible. Tertiary one is the better one here than the secondary carbocation. So that goes with the stereo specificity. And now the Br cyclic bond opens, the bridging bond opens, and you will end up with here the cyclopentane ring, methyl cyclopentane ring. Cl is attached to the downside, the bottom of the tertiary carbocation, and the Br is attached to the secondary carbocation now. So now the hydrogen was kind of not shown before, but you know the hydrogen was coming out in the reactant, but here the hydrogen is looking down basically. So that's how you want to see the 3D nature. You can put the sticks on them too, up and down, that's fine too. Now, so we're going to look at another situation for stereo specificity. Let's say cyclohexene ring, if it is reacted with bromine, in this case only bromine, I want to show you something different. So the electrophile, again, one of the bromines, the nucleophile is actually the pi bond, right? And it hits on the Br delta plus and opens up the Br covalent bond. You end up with the cyclic bromonium. Now here the cyclobromonium could be sticking up or sticking down, right? So that's the simplest way I can put this. So let's say this one is coming out of the flat, if you think looking from the top of the cyclohexane ring, sticking up, this bromonium is sticking down. And also the possibility of making this two types of cyclobromonium is 1-to-1, and still we have the Br negative, the bromide nucleophile to attack. So it's going to attack whatever the possible path, for the top one from the bottom, for the bottom one from the top, right? Now these are the products we're going to get. So we're going to get 2 different products. So what's that? So you will have solid Br and the dash Br. For this one, you will have dash Br and the solid Br. Now, if you look at, you get 1-to-1 of each molecule products. And what's the relationship between these two? Actually, they are object and mirror images of each other. So if you cannot see this way, you can define the RNS. It's an enantiomer pair. And also, this is 1-to-1, we said, producing, right? So therefore, it's a racemic mixture. When the enantiomer pair 1-to-1, it's a racemic mixture. And also, don't forget, this will show 0 optical rotation. Why 0? Because 50% of the products will cancel out the other 50% of the product, the optical activity, right? So that's what, so stop the video, go back and see whether you can really digest that idea. Okay, so next one, we're going to look at a different representation of cis-2 butene. Now, in this one, so we should be getting a racemic mixture. So as a homework, just practice question, just try whether you can actually make the racemic mixture for the cis-2-butene. Now, if you get the trans-2-butene, let's put it this should be a hydrogen actually, and yes. So that's a trans-2-butene, so cis and trans, and so it's flat molecules drawn and then reacted with bromine, and see, this one you should end up with the meso compound. Now, racemic mixture, you can follow the previous question and the answer. For the meso, I'm going to show you how does it look like. So here, if I simply think we did the two-step mechanism and we ended up with the product, let's say possibility of bromine going up or down doesn't really matter. And what happens here, let's say the bromine, the anti-addition happened, one bromine up, one bromine down, right? So in this case, what happens, if I get the R and S configuration, bromine is 1, CBr is 2, and methyl is 3. So you take the optical rotation clockwise, it's an R, right? So you can slowly do the, let's erase this one clear a little bit better, you can see that. And you can try the same thing for the other carbon. This is Br is 1, CBr is 2, and methyl is 3. Take the rotation 1, 2, 3. And there it looks R clockwise, but the hydrogen is in the foreground, so therefore flip it. So that should be S then, because the hydrogen is in the foreground, right? So therefore R and S like that for this molecule. So it's a symmetric molecule. You have R and S in the middle. So basically, the mirror plane sits in the middle of the molecule, right? So that's why it's a meso. At least two asymmetric centers, opposite absolute configurations, and also you can think there is if I clear this one and show you the point of inversion is in the middle of the molecule. You can actually rotate about and makes the mirror plane, or look at the point of inversion. The Br goes up to the left, Br goes down to the right likewise. So that's the point of inversion. So the point of inversion and the mirror plane sitting on the center of the molecule is the sign of meso, and sp3 two chiral centers, right? Okay, so the last question we got is the halohydrine formation. So the halohydrine, halo for the X, which is Br and Cl typically, and hydrine for the water, right? So again, we have an alkene. We're going to add electrophilic addition onto that. So in this case, we have a cyclopentene ring, and we're going to add bromine. In this case, Br2. It's a Br to show that delta plus delta minus, right? So which is double bond is near. It will be basically making transiently the delta plus on the Br, otherwise it's a non-polar molecule Br2. Now it's a polar molecule, right? Transiently. But you do have the water. Water is going to be the nucleophile, because water is a lot of water, there's abundance of water. And the nature, let's see when we attack that one. So you're going to make the cyclic bromonium again. And it could be, I'm going to put the dashed dotted lines, just it could be up or down, cyclic bromonium, right? Now the Br minus is only few there, and let's say it's negative, it's stable, octet complete Br minus. But water is abundant and it's a better nucleophile in this scenario. That's the one going to attack to the carbocation. Either it's both secondary, it's symmetric, right? Either one is fine. Now we're going to end up with the product, the anti-product on the cyclopentane ring. So one Br is, in this case, if it is up, it would be down. If it is down, it would be up, right? And so you will see the anti-addition of water, OH, actually, because there is a deprotonation. So minus of the H plus from the water eventually, right? And that's a different step, acid-base step actually, right? But the Br is sticking down in this case. It could be other way around too, depending on how you did the cyclic bromonium.